So today's lesson goes kind of hand in hand with discs and washers and volume, because today we are finding volume of things. And I'm going to show you, so in past years, I've done a project after the AP exam. I haven't done it the last couple of years, but I've done a project. What's going to happen today is this. I want to show you guys just an idea of kind of what we're doing. You're not going to be making these, but this is what's going to be happening. We're going to be finding volume of things, okay? But certain types of things. You don't need to write this right now. I want to explain kind of the idea behind today. So today, here's what's going to happen. The problem is going to define a region, an area in the coordinate plane, kind of like with discs and washers. They would define a 2D region and then they would spin it, right? Well, today, you're going to start with some region in the coordinate plane. So let's say like that's our region right there. What's going to happen is you're going to fill this region up with cross sections that are things that you know how to find the areas of. It's called volumes of known cross sections. So the problem is going to define a 2D region, and then it's going to say, hey, I want you to put squares in there. Now, I am a terrible artist, and I'm terrible at getting the visualization across. I did find this Khan Academy video. It's like 4 minutes, but he does an awesome job of driving the graphic home of exactly what's happening. But before I show that video, I'll do my best to explain. So I want you to imagine that I have this square. In fact, I want to just rip one of these off. What? No. Just one. You wouldn't even know. If I didn't tell you I just ripped it off, you wouldn't even know it was gone. Bethany Gammon. That's Matthew's sister. I had Matthew. I can't remember if he's Matthew. Your sister made this one.
Imagine that.
She's gonna be mad at me. Don't tell her.
Okay.
I took off one of the squares.
All right.
So what's gonna happen is this. Okay, imagine I take the square, and I'm like, I want to fill up this region right here. It's gonna be kind of hard to see with a whole bunch of squares. Now it's hard to tell because it's coming off the paper. So for you guys, you can see here, I put this in the plane and it's coming straight off the paper, right? Now you're confined how far that square can come off the paper since it's a square. Like imagine that the edge of the square, this particular one, is right here. Well, since it's a square, however long that is, it can only come off the paper that distance because the sides have to be the same. So sometimes they're going to say put squares in there. Sometimes they're going to say put isosceles right triangles in there. Isosceles because however long the base is, it can only come off the paper that same distance. The sides have to be the same. Or sometimes it might say put a rectangle in there, but they put a stipulation on that. Because if I put a rectangle in there, well, now it can come off the paper as far as I want it to. You're not constrained. So what they'll do, they'll say, put a rectangle in there, but the height is 3 times the base. So it can only come out 3 times of whatever that length is. So you're going to be filling things in that we know how to find the areas of. So squares, rectangles, triangles, semicircles. Those are the only things I've ever seen. You're going to put in squares, rectangles, triangles, semicircles. Then we're going to be finding the volume of one of these things. See how this has some thickness to it? I'm basically going to be finding the volume of this thing and then integrating to find the volume of all those squares. That's what integration does. That's the idea today. It goes hand in hand with last lesson because what we did last time, we found the volume of cylinders and then we added up a whole bunch of cylinder volumes. But it was cylinders every single time. Today, those shapes are going to be different. There are a lot of calculus teachers that actually do this lesson before discs and washers. I'm actually debating on that. I think next year I'm going to for a couple of different reasons I'll explain as the lesson goes on. But again, to get you to understand kind of the idea today, the concept, I'm going to have my buddy Sal Khan explain just really quick 4-minute. For some reason, he does a really good job of visualizing this and getting into what the formula is. So that's what I'm going to do. Source search, stop share, new share, share screen, AirPlay. Matthew, you're going to tell her, aren't you?
I just texted her. She said she's mad at you.
No, you didn't. Are you serious?
Yep.
No?
Yeah, no, I'm serious.
You are serious?
Yep.
I don't believe you, but part of me believes you.
Okay.
All right. So it is 5 minutes. We're not going to watch all of it, though. We're only going to watch the first 4. Oh, look at over here. Understand calculus in 35 minutes. If you guys want to know calculus in 35 minutes, here's the organic chemistry tutor. I think they use calculus in there. He does have some good videos. I show some of them in BC. He has a lot of just good examples. I'm going to watch that in AL. I'm not joking. Just curious what he has to say. Okay. So here's Sal.
Already familiar with
Thought everyone
finding
did.
the area between curves. And in fact, if you're not, I encourage you to review that on Khan Academy. For example, we can find this yellow area using a definite integral. But what we're going to do in this video is do something even more interesting. We're going to find the volume of shapes where the base is defined in some way by the area between two curves. And in this video, we're going to think about a shape. And I'm going to draw it in 3 dimensions. So let me draw this over again, but with a little bit of perspective. So let's make this the y-axis. So that's the y-axis. This is my x-axis. That is my x-axis. This is the line y is equal to 6. Right over there, y is equal to 6. And this dotted line, you could just draw it like this. And so this would be the point x equals 2. And then the graph of y is equal to 4 times the natural log of 3 minus x would look something like this. And so this region is this region. But it's going to be the base of a 3-dimensional shape where any cross section, if I were to take a cross section right over here, is going to be a square. So whatever this length is, we also go that much high. And so the cross section is a square right over there.
Isn't that much
The
better?
cross section right over here is going to be a square. Whatever the difference between these two functions is, that's also how high we are going to go. This length, which is 6 at this point, this is also going to be the height. It is going to be a square. It's going to be quite big. Let's scroll down so we can draw the whole thing roughly at the right proportion. So it looks something like this. This should be a square. It looks something like this. And so the whole shape would look something like this. Would look something like that. Try to shape that in a little bit so that you can appreciate it a little bit more. But hopefully you get the idea. And some of you might be excited and some of you might be a little intimidated. Well, hey, I've been dealing with the 2 dimensions for so long. What's going on with these 3 dimensions? But you'll quickly appreciate that you already have the powers of integration to solve this. And to do that, we just have to break up the shape into a bunch of these. You can view them as these little square tiles that have some depth to them. So let's make that into a little tile, this one into it that also has some depth to it. You could even, I could draw it in multiple places. You could view this as break it up into these things that have a very small depth that we could call dx. And we know how to figure out what their volume is. What would be the volume of one of these things? Well, it would be the depth times the area times the surface area of this cross section right over here. We do a different color. So what would be the area that I am shading in pink right over here? Well, that area is going to be the base length squared. What's the base length? What's the difference between these two functions? It is going to be 6 minus, our bottom function is 4 times the natural log of 3 minus x. And so that would just give us that length. But if we square it, we get this entire area. We get that entire area, you square it. And then you multiply it times the depth. You multiply it times the depth. Now you have the volume of just this little section right over here. And I think you might see where this is going. Now, what if you were to add up all of these from x equals 0 to x equals 2? Well, then you would have the volume of the entire thing. This is the power of the definite integral. So we could just integrate from x equals 0 to x equals 2, from x equals 0 to x equals 2. If you drew where these intersect our base, you would say, all right, this thing right over here would be this thing right over here, where it's dx. And instead of just multiplying dx times the difference between these functions, we're going to square the difference of these functions because we're visualizing this three-dimensional shape, the surface area of this three-dimensional shape, as opposed to just the height of this little rectangle. And if you were to evaluate this integral, you would indeed get the volume of this kind of pedestal horn looking thing. This is not an easy definite integral.
So I thought that was a lot better than anything I could ever do to get you guys to see these symbols. I used to show a different video of this guy. He was so boring, but he had this computer program and he would like use the program to create these three-dimensional figures. You can see it in action, but for some reason the video is gone. So I found this one, which I think does a really good job too, of just visualizing exactly what's happening. Okay. So if you guys can find the area of a square, the area of a triangle, the area of a semicircle, and the area of a rectangle, those are the four things you need to know today. Those are the four area formulas you guys have to know. All right. So let's jump to the notes. Thank you, Sal. How many of you guys knew his name was Sal? Yeah. See, how did you not know?
Why would I know?
Popular dude. Good guy. You know his last name's Khan because what? Oh.
But like there are other people that make videos.
Do you know why he started making videos?
No.
His nephew, I think it was in a math class struggling like overseas, and he was like helping him out. So just making all these videos. And then he realized he had a pretty good gift, and then he just made it blew up from that. That's how it all started. Does he? He does bio and chemistry? Holy smokes. He is smart. And econ. That doesn't even seem to fit in there.
Oh yeah, I remember watching this.
That's crazy. Well, good for him. Okay. Government. So that's what we're doing today. There's only one volume formula that you guys have to know today. Just one. And here's what it is. So if your cross sections are perpendicular to the x-axis, you know how when we did discs and washers, we had to decide, are we in terms of x's or y's? We also have to take that into consideration with cross sections. The problem's either going to tell you, so if you look here at example 1, it's either going to tell you they're perpendicular to the x-axis, or they're going to tell you it's perpendicular to the y-axis. The problem will tell you that. If it's perpendicular to the x-axis, everything is in terms of x values. Your limits of integration are x's, your functions are in terms of x, and then if it's perpendicular to the y-axis, vice versa. So here's our formula. If we are doing cross sections perpendicular to the x-axis, we are going to integrate from a to b. And what we're going to do, instead of me putting a of x in here, I'm going to do it this way to start off with. The way you guys find volume of any prism ever, in geometry, you should have learned it's the area of the base times the height. That's how you find the volume of any prism ever. And last class, or 2 classes ago with discs and washers, our formula was always pi r squared times the height for a cylinder. The reason it was that for cylinders is if I do area of the base times the height, and I'm talking about a cylinder, well, the base is always a circle on a cylinder. The area of a circle is always pi r squared. That's why we were using that formula every single time. We were doing the same thing we're doing today. It's just every time it was a cylinder. So we use the same formula every single time. Today, if you're doing a square versus a triangle versus a semicircle, your area formula changes a little bit, which that's what we're going to practice. That's what we're going to get into. So what that leads to is this. It's a of x, whatever the area is, that's what we're going to find. And then the height is dx. The height is represented by dx. And that is us integrating volume of these prisms, whatever the prisms are. Notice there's no pi in the formula. This is one reason a lot of calc teachers say they do this lesson first, because you guys just spent 2 straight classes where pi was in every single problem you did. It was always pi and then r squared, or big R squared minus little r squared, but pi was in every single one. It's because they were always cylinders. So pi was in every one. But in these, if we're doing squares or rectangles or triangles, there's no pi involved at all in these problems. I do have students that screw up and put pi on these problems, but calc teachers that say they do this lesson first say they find a lot fewer students mess that up. So that's one reason why I'm debating on putting this first. If we're perpendicular to the y-axis, same thing. It's just now we're all in terms of y. All right. So we got 4 examples to do. Let's do it. Find the volume of the region whose base is bounded by x cubed, y equals 0, and x equals 1. So the first thing the problem has to do is give you your 2D region in the coordinate plane. Like they have to define the space that you're going to be filling up with these figures anyway. So I'm going to draw that. So we need the region that's bounded by y equals x cubed. So that's like, oh no, I missed the origin. Oh, that's just bad. I apologize. I don't know why I'm so bad at that. In middle school, we had to choose between choir and art. And I am a terrible singer, but I took choir. And you can see why. You got an A if you just went to the concert. You didn't have to sing. You just stand there and act like you're singing, you get an A. But in art, you have to draw something. I can't. So choir it was. All right. Y equals 0 is the x-axis. And then x equals 1. I'll just put that right here. Okay. So our region is this little space right there. That's what we're going to fill up. And we're going to fill it up with squares that are perpendicular to the x-axis. So again, imagine I take this little square right here and I plop it straight down onto the paper. So it's coming off the paper. This is what I am not good at doing, but I'm good at doing the math, but not the drawing. So one side is there, and then it's going to come off the paper that same amount because it's a square. Like that. That's not terrible. Is this terrible?
I can't tell.
You can't see it?
I can see it. It's like uncomfortable.
Okay. So here is how I'm going to go about this problem. I know that I have to find the area of the square. That's the main thing. So I always start with what is the area formula of the cross section? How do we find the area of a square? Base times height, but I'm not going to put base times height because since it's a square, what do I know about the base and the height? They're the same. So I wouldn't put base times height. It's not wrong, but I would put like base squared or side squared or something squared to let you know we just have to find that side. So I always start with writing the actual area formula of my figure. In general, a square is side squared. Okay. Our job is to figure out this. This is kind of, I don't want to, I guess I should say the hardest part of the problem, but kind of like with discs and washers, finding the R's, those were the hardest parts of the problem. That's the same thing here. I need to figure out what is that side length. So the side length is however long this little length is right here in the coordinate plane. How long is that length right there? No matter where I draw it, I could draw it here or here. How long is that red bar? It's x cubed. It's the function. So the side is the function. So then my next step is I do this. You don't have to do it the way I'm doing it. This just helps me. I write the area formula for the figure. And then I have to find that independent variable, that side. It's x cubed, which means then the area is x cubed squared. So x to the 6th. That is what we are going to integrate. Whatever the area is in terms of the functions, just plop that in the integral and off you go. There's no pi involved. Our volume is going to be the integral from 0 to 1. And we just plop the area formula right inside of there. Because this is the area of the base. That's what x to the 6th is. And dx is the height. That's us integrating volume. of one of these. Imagine it being a really minuscule prism. And we just do the problem. Notice there's no pi because we're not rotating anything. There's no circles involved. That's it. We're going to do this one by hand. All the rest we'll use with our calculator. I always want to do one by hand because on the last test it wasn't a lot of students, but it was still too many. I had students that would forget to integrate first. It's common, but I would have students just plug in the 1 and the 0 now. Make sure you integrate. So 1/7 x to the 7th from 0 to 1. Plug in the 1. So 1/7. That's the volume of that figure that would get created. What do you guys think? Next, all right. Find the volume of the same solid as example 1, but now those squares are going to be perpendicular to the y-axis. So I'm going to redraw that region. So I'm just going to show you what I did. So it's the same region. Oh, don't look at that one on the right. But I also don't want to show the work. Touch. Like a magician, like Mr. Cecil. So it's the same region, but now those squares I put in, that base is perpendicular to the y-axis. Is that one better, Jacob? Can you visualize that one better, or is it worse? I don't know. Without like being able to tilt how he did with his coordinate plane, I don't know how to. Yeah, I think so. What's that? Isometric. That's what that's called. Like CAD programs. You guys do CAD still, or is that gone? Okay. So here we go. So I have that figure. I gotta redraw it anyways. That was stupid. Just stupid. Okay. So first things first, since we're perpendicular to the y-axis, that tells me a couple of things. Number one, I have to change my equations to be in terms of y values now. So you know how it started as y equals x cubed? Well, now we have to solve that for x. So cube root both sides. X equals the cube root of y. That's the function we're going to be working with instead when we plug this stuff in. Cube root of y. Okay. So the area is still side squared. It's still a square, so it's still side squared. But this one's different because that side length is not just a function this time. I'm after this thing right here. How long is that bar? What's the length of this thing right here? One minus the cube root of y. Yeah, 1 minus the cube root of y. The other reason calc teachers, I really think I'm going to push this in front of discs and washers. The other reason calc teachers put this in front of discs and washers is because to find these lengths right here, you're just subtracting the two functions, which comes right off the heels of finding area between two curves when you're just subtracting the functions. So that's what's happening. So I do think in the book it puts it after, but I think I'm going to put it in front. I think I've convinced myself. So this is just 1 minus the cube root of y. You're just subtracting your two functions. We did that here anyway. We did that on the previous problem. It just so happened the bottom function was 0 because it was the x-axis. So we did it on the last one. So the side is going to be 1 minus the cube root of y, which means then the area is that side 1 minus the cube root of y squared. And that's the thing that goes inside the integral. That's what we're after. We write our area formula, we figure out the side length, we figure out the actual area formula, and we plug that into the integral. So we're going to be integrating 1 minus the cube root of y all squared dy. I got to find my limits of integration though. So our limits of integration have to be y values from bottom to top. So we're still integrating from 0, because that's our bottom value. And then we're integrating up to this y value. Thanks. We still have to find that y value. We can find that y value because this point is really just whatever the x cubed function is when x is 1. When x is 1, then the y value is also 1. So we are integrating from 0 to 1, but I wanted to drive the idea home. These are y values, not x values. We are going to do this with calculator, but let's say you did have to do this by hand. Please, oh please, oh please, oh please, do not distribute this 2 into the parentheses. Please do not do that. That would make me sad. So I'm just going to math 9 this bad boy. And we get 0.009 or 0.099, I lied. Stupid decimal. My son got his report card yesterday from Hinkle. So they get 1s, 2s, or 3s on like all these standards. And in language arts, he had all 3s. And in math, he had all 3s. And he got a 1 in comparing decimals.
Oh.
It's because the week before they had a worksheet where they had to compare like 0.5 to 0.50. And he didn't know those were the same. Now he does.
You got a 1, did you miss that?
He missed 2 of them.
Oh, okay.
He missed another one. Oh, they did. There was one like this. And he thought this one was bigger because it had more numbers. But now he knows. We talked through it. So he didn't get dinner that night. He got his report done. What's that? All right, we got 2 left. Well, that's true. Find the volume of the solid whose base is bounded by the graphs of y equals x plus 1 and y equals x squared minus 1. So they're giving you that 2D plane. And then you're going to fill it up with isosceles right triangles with one of the legs perpendicular to the x-axis. I have one of the projects that year, they did that. So this one right here looks kind of cool. This is a lot of right triangles that are filled in. So you could see like the base, and then you could see the triangle go straight up off. It's hard for you guys to see that at home, but so that's kind of what's happening here. That's a whole bunch of right triangles that are filling in this 2D space. That's what's happening. So the first thing I'm going to do is draw that region. So I'm going to graph y equals x plus 1. It's just a rough sketch. So the y-intercept's 1, the slope is 1. So like that. And then y equals x squared minus 1. So that's your parabola shifted down 1 unit. That's your normal parabola shifted down. Again, it's just a rough sketch. We don't have to be pretty with this. So something like this. And we're not bounded by the axes at all. So we're actually between these 2 curves. This is the region that we're filling up with isosceles right triangles. So again, what's going to happen is we have a leg like this. And then since it's isosceles, it's going to come off the paper that same distance. That's what I talk about with constraints. Like it can't just come off the paper as far as it wants. It can only come off the paper that same height. Okay. No?
That's what a little bit.
I thought the first one was good. I think it's good.
Thanks. You guys are just trying to make me feel better. Okay. So I'm going to start the same way I have on all these. I start with what is the area formula of these things? The first one was just side squared. So it was a square. But this one's different. What's the area formula? Well, first of all, what's the area formula of a triangle in general? 1/2 base times height. So we all need to know that. But this one's even more specific than that because it's isosceles. The base and the height are the same. So instead of putting 1/2 base times height, you could put 1/2 base squared or 1/2 side squared or whatever you want to put. That's completely up to you. I wouldn't put x though, because x is already defined in the functions. I would use any other letter. So I'll do 1/2 side squared. Now we just have to figure out that side length. Your side length is always going to be the difference in your functions. Like this side length right here is just the top function minus the bottom function. That's how long that thing is. So our side is x plus 1 minus the quantity x squared minus 1. If you put it in parentheses. I would clean that up. I mean, this is going to go in right here for S, but I would clean it up first, especially if you're going to enter this in your calculator. You want it to be as neat as possible to avoid any parenthesis issues. So what's that going to be? Negative x squared plus x, 1 minus negative 1 is 2. So that's our side. And then we just pop that right in for S. So our area is going to be 1/2 that thing squared. That is what's going to go inside the integral. Again, notice no pi involved. But don't forget when you do your discs and washers to do pi. And I think on the review, I put the review on Canvas, I think last time. I think I tried throughout the review to mix them up to keep you on your toes. So it wasn't like all discs and then cross sections. I think they're all sprinkled in. So you guys have to think about, does it need pi or not? I did that for you guys. You're welcome. I think I did anyway. I don't know. Maybe I didn't. All I have to find now are my limits of integration. So I have to figure out what are these x coordinates here and here. And anytime you're finding intersections, this is solving a system. If you have a calculator, if it's a calculator active problem, you can use your calculator to find those intersection points. You don't have to solve the system. Just like you don't have to integrate by hand, you don't have to differentiate by hand, you don't have to solve equations by hand, and you don't have to solve systems by hand. They let you use your calculator to do all that work. Unfortunately, we're going to solve the system. To remind you guys how. I'm going to set those two things equal. Got ourselves a lovely little quadratic. So I'm going to set it equal to 0. I'm going to move everything to the right side. I'm going to keep x squared positive. Factor that bad boy. We're integrating from -1 to 2. I'm just going to do that with the calculator. Beep, bop, boop, math 9. On my key, I put 4.05. Is that right? To 3 places? Was it like 4 point?
It's just 4.05.
Oh, that's legit the number?
Yep.
That's crazy. Got all that messiness going on. And it's, yeah.
Where did this? Now for area 1.
What are you talking about? What do you mean? Where'd the square go? It's right there. It's been there all along. I screwed up. Got one more. The last thing, the last example. I know. Take a moment. Okay. Crazy that I'm done teaching calculus after this block. Multiple choice. I did, and that's the answer. So I had the first year I put this one on last year, and the thing didn't have C there, and we did the problem. Oh, I still remember. It was a crap show. We finished the problem, and I was like, the answer's not there. Then I realized what happened. The choice didn't transfer over. So C is the right answer, but when in doubt, guess C, right? Okay, the base of the solid is the region in the first quadrant shown over here in the graph, bounded by the x-axis, y-axis, and the line x plus 2y equals 8. So that's that line. Cross sections of the solid are perpendicular to the x-axis. They are semicircles this time. So now pi is going to be involved because the area of a semicircle or circles in general has pi in it. So pi will enter the picture here. What's the volume of the solid? So since it's perpendicular to the x-axis, the very first thing I do, I take any equation in the problem and I solve it for y. That would be step number 1 for me. I start there. So it's perpendicular to the x-axis. I'm going to solve that line equation for y. So I'm going to subtract x and divide everything by 2. So that's the equation of the line that I'm going to be using. To give you a great visual of what's happening here, we're plopping semicircles into this thing, which I have an example of that right here. So they have this region, and then those are semicircles, so half the circle that get plopped on to that coordinate plane. So you guys there's a whole bunch of semicircles sticking off the board. And again, since it's a circle, you're confined how far off the paper it can go, because the radius has to be the same. So in general, it's perpendicular to the x-axis, and then it comes off the paper. This is my worst one because it's so gray, and I don't know. Whatever. Doesn't even matter. Like, you don't even need to draw these things. You know what I draw. Okay. There's a reason why I draw this one for the radius. So I'm going to go through my 3-step process. Step 1, I write the area formula for whatever the cross section is. So the area formula for a semicircle, well, a circle is pi r squared. So a semicircle is 1/2 pi r squared. So on the square problems, we had to find s. On the triangle problem, we had to find s. On this problem, we have to find r. This one's a little tricky. I'll explain why. So it's very common that students would think r to be -1/2 x plus 4. But what is -1/2 x plus 4? That's the diameter of the circle. This length right here from the line to the x-axis, which is what this is the diameter of that semicircle, and that's not what I want. So the radius is half of that. This is the diameter. The radius is 1/2 of that. The reason this one's tricky is because there's actually 3 1/2s in the problem. There's a 1/2 here in the area formula. And now for the radius, there's 2 1/2s that enter the picture. It's just a tricky problem because of how many 1/2s there are. But I'm just going to plop this right over here in for r. I would probably distribute first, clean it up a little bit. So that's my radius. That is going to come right here. So it's 1/2 pi, and then times that radius squared. That area is what goes inside the integral. And it's x's, so we're integrating from 0 to 8. And then when you do enter this in the calculator, just pay careful attention to the parentheses and stuff. I would make sure that you're able to enter. There's nothing worse than having it set up right and you get the wrong answer. That happened to people a lot on the last test. I don't know if it was entering things wrong or parentheses. I'm not sure, but the answer to this is C. And that's it. You've learned all of calculus. Calc 1 anyway. There's Calc 2 and Calc 3 still that you guys will come across. Yeah. Well, I bet that's just Calc 1.
Well, we'll find out. once he
I will find out right after I turn this off. I'm gonna watch it.
does.
I'm curious what he has to say. I mean, calculus in general, I could teach it in 1 minute. Huh?
Why have I been here for 7 months?
All right. So I'm done. Your homework tonight, I found, I think it's five good questions on AP Classroom. I think they're multiple choice, but just like 5 different types of questions. So it's pretty good worksheet. I think I put the solutions on there too. So Thursday we'll review, and then our test is next week. So you guys in here luck out because your test is Monday, and then you have nothing after that for the week. Like you won't have e-learning next week, and you're not going to have anything at home on Friday when they're testing. So you guys test Monday, and then you're off for spring break, at least from calculus. You guys at home will be in class for review, and then your test won't be until the following Friday, which sucks. But what can you do? I don't know. All right, you guys are free to go. Peace out.